Recording. Okay, so thank you as always every week for being here. Merry Christmas, Happy New Year. This should be a happy time of year for everybody, and thank you for being here. This will be our last session of the year, but we'll start right up again in 2 weeks. We'll just take next week off for Christmas and New Year's. One more reminder, can you please type your name into the chat now? So that I have your record for attendance. Anybody who typed it in before, it's not recorded. So now that I started recording, you can type your name in and let me write that down. So please type your name into the chat. Zoom chat. Okay, good. And I need to see one more thing before I start. Just need the diagram. Here we go. Okay, so welcome again, everybody. Thank you for coming. And yeah, so we're going to start like we usually do, going over some of the homework. And then today we're going to stop talking about triangles and we're going to talk a little bit about quadrilaterals today. And then we'll finish our polygon unit next time, which will be in 2 weeks because we'll skip next week. Okay, so I was very happy to see a few people hand in solutions to the homework, which were mostly correct, although there are going to be little extra answers that you can have. So let's talk about this first problem. So we have a triangle with side lengths 4, 6, and 9. So this triangle's, it's not going to be a right angled triangle. It's going to look something like this. Maybe that's not a good picture. Let me try something a little bigger. If this is 6, this is 4. Yeah, it may look something like this. So 4, 6, and 9. Okay. So the question is, we have another triangle that's similar, and it has side lengths 8 and 12. So one way of drawing this would be to draw, a bigger triangle like this. That's also going to be similar, and it has side lengths 8 and 12. And so some people wrote, okay, so this is 8 here, and this is 12. And the question is asking, what are the possible lengths for the third side, right? So we have this question mark over here. What are the lengths for the third side, right? And let's just recall that similar triangles have a common ratio. So if we look at the respective sides, we get that the ratio 8 to 4 is the same as the ratio 12 to 6, which is the same as the ratio question mark to 9. And since we're all adults here, we won't call it question mark, we'll call it X. Okay, so what we have with this common ratio, this tells us that 8 over 4 is equal to 12 over 6 is equal to X over 9. And so what does that tell us when we solve for X? What do we get?
We'll get 18.
18, right. So we get X equals 18. So this is definitely a correct answer. You can have X equals 18 over here, right? Because you have the 8 to 4 and the 12 to 6, right? All of these things here are equal to 2, right? So if 2 is equal to 8 over 4 and 12 over 6, it's X over 9. If you just want to show the work, 2 is equal to X over 9, and we multiply both sides by 9, and we get 18 equals X. So that's completely fine. So 18 is definitely an answer to this question. Now, did anybody get, I claim there's a second answer that's also correct. Did anybody get a second answer, a different answer for this question than 18? And what I'm going to do is I'm going to draw the same triangle again. So I labeled this side 8 and this side 12. But is there maybe some other way that I could label the 8 and the 12 on the triangle? So 27, I see. Harrison, what's the reasoning for 27 being another answer?
Okay, so at this point, you're going to draw the triangle in another form, wherein the ratio becomes 4 to 12 and 9 to x.
So okay, so you want me to do 12 over here and x over here.
12.
Right. So
Yes.
this is 4 to 12, right? So you want the 12 down here, right?
Yeah.
And now you want the x to correspond to the 9, right?
Yeah.
So what's the problem here though? What does this side have to be?
27.
Well, no. The x you're saying is going to be 27. What is this side going to have to be? The side
9.
that I didn't. Well, remember, the problem said that the triangle has sides 8 and 12, right? So if this is 12 and this is 27.
It's 12. It's
right?
12.
Right. So, but that means this guy has to be 8, right? Because the question says the triangle is side lengths 8 and 12. And then the problem is, look at this. 12 to 4 is a ratio of 3. But 8 to 6 is not a ratio of 3, right? So that means that if I label the triangle like this, then these two triangles are not similar.
Yeah,
right? So I can't have a 12 and then an x, right? So it's a great idea, but it doesn't quite work because the triangles end up being not similar because the ratio is not common. 12 to 4 is not the same as 8 to 6. But the idea is completely right. So let's just do this slightly differently. Instead of putting a 12 here, how should we label it? Instead of 4 to 8, what happens if we put the x over here? Then where's the 8 and where's the 12?
The 12 now will be placed on the right, the longest side there.
Exactly, right?
Yeah.
And then the 8 is over here. And now what do we have? We have 8 to 6, right? Because this is 8 to 6. And then 12 to 9, these are the same, right? 12 over 9 is the same thing as 8 over 6. They're both the same as 4 over 3, right? So 8 over 6 here is equal to 12 over 9. And that's going to be equal to x over 4.
Perfect.
Yes, Harrison?
No, I said perfect.
Okay, perfect, right. So now we can cross multiply with whatever equation we want. So I can do 12 times 4 equals x times 9. So this gives us 12 times 4 equals x times 9, or in other words, 48 equals 9x, or this tells us, just going to go for a space, so x equals 48 over 9, which is the same thing as 16 over 3. So it turns out for this triangle, 16 over 3 is also a valid answer. So there's two possible answers over here. You can get x equals 18 if you label the triangle this way, or you can get x equals 16 over 3 if you label the triangle this way, right? And in both cases, you have similar triangles. What you're not allowed to do is put the x where the 8 is, because then if you try to label the 12 and the 8 over here, you're not going to get similar triangles because the 12 to 9 and the x to 4 won't work. So these are the only two ways you can label the triangle that are going to make it similar. Okay, 36 is not going to work because, again, if you put an x over here for 36, you're not going to be able to label these other two sides as 12 and 8 and keep the triangles similar. Yeah, so the only way you can get similar triangles is by putting the 12 and the 8 in these two arrangements here. Okay. The point being, 12 to 8, the ratio is the same as 3 to 2. So among these sides, you have to pick two sides that are in the ratio of 3 to 2. So you have two choices. You can pick the 9 and the 6. Those are in the ratio of 3 to 2. And so the 12 and 8 can correspond to that. Or you can pick the 6 and the 4. Those are in a ratio of 3 to 2. So the 12 and the 8 are going to correspond to that. You can't pick the 9 and the 4 because those are not in the ratio 3 to 2. So you can't have a 12 corresponding to the 9 and an 8 corresponding to the 4. Because then the triangles won't be similar. You won't get a common ratio. Okay, so this is a tricky problem. Most people who handed in the answers found 18, but I think nobody found 16 over 3. as another answer. So it's tricky to see, but both of these are actually correct answers. With the information I gave you, you don't know whether you know that there's two possibilities, either 18 or 16 over 3, because I didn't tell you what the corresponding sides are. I just told you that this triangle has side lengths 8 and 12. Okay. So any questions on this problem? No. Sorry, I'm not getting you so clearly, Gabriel.
As I was thinking,
Yes, Gabriel. Yeah, it's a little staticky. Yeah. Sorry, you're
I
not...
was thinking in a way.
Okay, good. I'm glad. So Kaifala has a question. Sorry, I'm not getting you so clearly. Maybe you need to type something. Kaifala, good question. So does the Pythagorean theorem work in this case? The answer is no, because this is not a right triangle here, right? If I try to do a squared plus b squared equals c squared, I get 4 squared plus 6 squared. That's 16 plus 36 is 52. But 9 squared is 81, right? So 52 is not equal to 81. So this means this is not a right-angled triangle. And so none of these triangles are going to be right-angled triangles. And that means the Pythagorean theorem does not apply. So you can't use it in this problem because the triangles don't have a right angle. And you need a right angle to be able to use Pythagoras' theorem. Okay. Any other questions about this? Yes, James?
What guarantees the third triangle to be similar to the remaining two, looking at the
Right.
few changes?
Because look at the ratios, right? The similar triangles have the common ratio, right? So, right, we said similar triangles are the same if their angles are all the same. But another way to check that is to see if there's a common ratio for all of the sides. So for this triangle and this triangle, we can look at the ratios 8 over 6, x over 4, and 12 over 9. And we need all of those to be equal for the triangles to be similar. So 8 over 6 equals 12 over 9. That's fine, right? Both of these are equal to 4 over 3, or alternatively, you can cross multiply and you get 72 equals 72. So because these are equal, and because this has an x in it, as long as we choose the correct value of x, we can make this ratio equal as well. And so this is one way of checking similar triangles, is to check that you get a common ratio for all 3 pairs of corresponding sides, right? 8 to 6, 12 to 9, and x to 4, right? And you're okay because these two match. And so you just make the third match by choosing the right value of x. And same thing here. Here you have 12 to 6, 8 to 4, and x to 9. That's fine as long as you choose the correct x, which is x equals 18. But if I switch the 8 and the 12 here, that would be no good, because then I have 8 to 6 and 12 to 4, and those don't match, right? Those are 2 different ratios. So for similar triangles, you need all 3 ratios to be the same. For congruent triangles, you need all 3 ratios to be 1. For similar triangles, it's just good enough that they're the same. They don't have to be 1. They just have to be the same as each other. Right. Does that answer the question?
Yeah, I understand.
Okay, great. All right, any other questions on this? Yes, James.
Looking at the ratio, 8 over 6, when you have the ratio, that will be 4 over 3, and 12 over now before. But looking at x over 4, it goes as 16 over 3.
Yeah.
It is equal?
Yeah, so that's fine. I mean, if you have x equals 16 over 3, right, then 16 over 3 over 4 is 4 over 3. So it also fits in. It's completely fine. You have 16 over 3 divided by 4, and that exactly gives you 4 over 3. So it's just the same as 12 over 9 and 8 over 6, right? You're just solving for x here to make everything equal.
Yeah, so that value 16 was just the value of x. When you place it in the solution there, that will solve it to 4 over 3, right?
Exactly. So if you check by plugging in, you get that it's also 4 over 3, same as these other 2 ratios. Okay. Other questions? Okay, so let's move on to the second one. So we started quadrilaterals, so we have to find the angle in the following diagram. I'm just going to redraw the diagram. So we have a triangle that looks like this. And here we have 60 degrees, not a triangle, sorry, a quadrilateral, 60 degrees and 15 degrees and 20 degrees. And we want to find this missing angle over here. Okay, so does anybody want to give a solution here? Yes. Hello? Sorry. It's not coming clearly. Hi, Gabriel, we're not getting you. Hello? Yes. Sorry, not getting you. It's coming in and out. I'm not getting you.
Hello.
Hello, Abraham?
Yeah, that's it. Miss
Yeah. Abraham? Yep.
120 degree, the missing angle.
Okay, so your answer is 120 degrees. So how did you get that?
That's it. The angle at the top.
Right.
Double of it. Two of the angle at the top is equal to the center angle.
Ah, so I see. Right. So you're using the formula that this angle at the top is equal to twice, is one half the center angle. So
yeah, one half the center angle.
right. So this is a formula that we haven't talked about yet, right? So this is a formula that's valid if we had that this entire thing was inscribed in a circle, right? This is a formula from angles in a circle. So if this whole quadrilateral was inscribed in a circle, and if this was the center of the circle, then we would exactly have that formula that this angle here is half of this angle here, right? And we'd get an answer of 120. Now, the problem is I didn't tell you that, right? I didn't tell you that you can inscribe this in a circle like that. I mean, you can always inscribe a triangle in a circle, but I didn't tell you that this point is going to be the center of the circle, right? So maybe if I draw this like this, maybe this point is not the center of the circle, right? Actually, the way I drew it, it looks like this point is not the center of the circle, right? So the 120 would be correct if this were the center of the circle, but I'm not convinced that this point is the center of the circle. So it's a good formula to use, but I think we may end up getting a different answer. So does anybody have a different answer for this? I know a couple people handed this in. Well, so here's a first question. We know that the angles in a quadrilateral add to 360 degrees, right? So I have 15, I have 60, I have 20. How can I figure out this angle inside the quadrilateral, the green angle? So if the green angle is, let's say, x, then what equation can I set up for the green angle?
Yeah,
that.
Yeah, Ed?
is equal to
Yeah, I think I mean, I don't
15.
know what if I mean right.
No.
Okay, but if I look at this triangle, I
Mm-hmm.
can draw a parallelogram to have the 60 degree. I can carry upward, then I'll have the angle in the red to be remote angle.
Mm-hmm.
Then
So
with the remote angle, I can say the remote angle is equal to the sum of the 60 degree plus, I cannot see the one down.
Mm-hmm.
I mean, okay, about the 20 degree.
Mm-hmm.
What I'm saying, do I have the 20 degree?
Yep.
Do I have the 20 degree
Yeah, the 20
down?
degrees,
Yeah, I can draw, or maybe probably, or imaginary line going upward. Then that will form
Okay.
another angle over there. Then the two angle over there, the 60 and the 20, will make the
Mhm.
angle in the red to be remote angle.
Yeah, the
And the
remote
remote
angle.
because of the sum, the remote angle because of the sum of the 60 plus the 20.
Okay,
So that'll be 80 degrees.
80 degrees. Okay, so that's close, but I think you're going to have to add in the 15 degrees also in order to do that. So one thing that you can do, right, for setting this up is we know the
Mr. Over.
angles all add to, yeah, 3. Yes, sorry, Abraham?
Yeah. So let's say to find the green angle, which is the X,
Right.
we say the 15-degree angle plus the 60-degree angle plus the 20-degree angle
Right.
plus the X
Mhm.
is equivalent to 360.
Exactly, right?
Equation.
So we know everything adds to 360. So this green angle X, when you add it to all the other angles, it needs to be 360, right? So if you solve this, you get, this is 95 plus X equals 360. And then this will be X equals 360 minus 95, which is going to equal 265. Okay, so we'll say green angle if it's X degrees, right? So it's going to be 265. And so now, so if the green angle is X degrees, then how do we calculate the red angle?
Yeah. So we say, hello.
Yep.
Yeah, we say the red angle will be equal to the green angle minus 360 degrees. That is the
Right.
complete circle now.
Exactly. So, or 360 degrees minus the green angle, right? So the red angle is going to be 360 minus X, right? Because if this is the green angle, what we have is that, you know, in this case, red plus green equals 360 degrees because it makes a full cycle, right? So if the red angle here is 360 minus X, that's the same thing as 360 minus 265, and that's going to end up being 95 degrees. So this is actually the correct answer, is that this angle right here is 95 degrees. And what we see is actually this angle here is exactly the sum of all three of these angles. And this is true in general. If you draw a quadrilateral that looks like this, and you're asking for the kind of outside angle here, it's always just going to be the sum of the other three angles. Okay, and you can show it by using this method, right? Because all of them, this angle plus this angle is 360, but this angle also plus the sum of these three angles is 360. So that means this angle has to be the sum of these three angles. Okay. So yeah, so you actually get 95 degrees. It looks like it could be 120, but that would only be if this point was the center of the circle. And we'll talk a little bit about circles and inscribed angles and everything. We'll do that in a couple of weeks. But what this means actually is that this point is not the center of the circle if you inscribe the triangle in the circle. So this point is going to be a little bit away from the center of the circle. Okay. So this method is to first calculate the green angle using that the sum of the angles in a quadrilateral is 360, and then you calculate the red angle using that the red angle plus the green angle has to be equal to 360. Okay. So any questions about this problem?
Yeah, that was.
Yes, Francis.
Yeah, I'm catching a bit problem because if we look at the angle 60 degree plus 20 degree plus 15 degree, it will sum up the range of 75 degree.
95.
I'm seeing 95 there.
15
because
plus
15
yeah.
plus 20 is okay, good, 95.
It's okay?
Yeah, it's okay.
Okay, good. All right. Other questions?
Yeah, that over.
Yeah, James.
Yeah, normal can vary sometimes. So if you having that take about 15, 60, and 20 equal to the angle we are looking for, which is 95. If the number changes, we can get to that same number.
Yeah. So if I change this 15 to 25, for instance, so that these would add up to 105, then the red angle would also be 105. If I draw a picture like this, the red angle will always be the sum of the three blue angles. no matter what their measures are.
Yeah, I can ask a question. Yes, sir.
Yes, Prince.
Yeah, thank you. Yeah, that for instance, the angle here which is in green was
Yeah.
given. Then you don't have the red angle. That's for instance. So it's just that because of the total circle, will you just subtract the green angle from the red to get the angle of the red? Is what you will
Right.
simply do.
Yeah, the red and the green have to add up to 360 because they make a full cycle.
Okay.
Yeah, so no matter what, the red and the green is always going to add to 360 because they're always making a full cycle.
All right.
Other questions?
All right. Thank you.
Okay, you're welcome.
Hello.
Hello, yes.
Hello.
Yep, Princeton?
Yeah, Princeton. Yeah. Okay, my question is, why in case we have the green angle is given, the red is given, but on top there where we find 60 degrees not given?
Okay. So well, if either the green or the red is given, then you can easily find the other one because you just have to say that they add together to 360. So if you know the green or the red, then you don't even need to know any of the blue angles in order to get the other one. But we needed to first figure out the green angle and then figure out the red angle in this question.
Okay, thank you.
Okay. Yes.
Like why am I calling? For example, we know the red angle to be 95 is the sum of all the three angles. Like say the angle above is x, you don't know it. So can we sum everything to 95 and solve for the x, the angle that is not formed?
Yeah, exactly. Because it's the same thing because look, we have the same two equations basically, right? From the quadrilateral, we have 15 plus 16 plus 20 plus x equals 360. From the red and the green, right, we have so if x is the green angle, we add it to this 95, we get 360. Also, we add it to the red angle and we get 360. So that means we have the same angle. There's two different things we can add to it to get 360. We can either add the red angle, so we have the green angle, right? We can either add the red angle or we can add all three blue angles. Either way, it adds to 360. So since I can either add the red angle or I can add all three blue angles, either one gives me the same sum. That tells me that the red angle has to be the same as adding all three blue angles, no matter what, because both of them you can add to the green angle to get 360. Is that clearer?
Yeah, thank you.
Okay, you're welcome. Okay. Okay. Great. Okay, let's move on. Let's do some new stuff, okay? So I'll talk a little bit about quadrilaterals today. Oh yeah, please write your name if you haven't done it yet. You have any time during class to do it. So for the past 2 weeks, we studied triangles, which are polygons with 3 sides. So today we're going to discuss quadrilaterals, which are polygons with 4 sides, which get a little bit more complicated. So there's lots of different types of special quadrilaterals and lots of overlap between the different types. And so, for instance, unlike in the case of triangles, you can have all 4 sides of a quadrilateral being equal, but that doesn't mean that all the angles are going to be equal. And similarly, you can have all the angles equal, but that doesn't mean that all the sides are going to be equal, right? So with a triangle, if you have that all 3 sides are equal, you know that all 3 angles will be equal. It's an equilateral triangle. And you also know that if all 3 angles are equal, then all 3 sides are equal too. But for a quadrilateral, this is not the case. And what this means is we end up getting lots of different types of quadrilaterals. Okay, so here are all these different types of quadrilaterals that we get. Okay, let's see. So certain types of quadrilaterals. So you've heard of most of these. So a square, we all know what a square is. It's a quadrilateral with 4 sides equal and all 4 angles equal. And this means also so that all angles are right angles. Right? Because if all 4 angles are equal and they add to 360, that means each one is 90 degrees. So a rectangle is a quadrilateral with all four angles equal, but not necessarily all four sides equal, right? So I'll just draw a picture of each one. This is a square. A rectangle might look like this. So it still has four right angles, but not necessarily all four sides equal. A rhombus is if you do the other thing. So if you have a quadrilateral with all four sides equal, but not necessarily all four angles equal. So a rhombus could look like this, right? If I draw this, sometimes it's called a diamond, right? A rhombus looks like a diamond. All four of these sides have equal lengths, but the angles are definitely not equal, right? This angle over here is smaller than this angle over here, right? This is a bigger angle. So that's called a rhombus. A parallelogram is a quadrilateral with two pairs of parallel sides. And it turns out that if you have two pairs of parallel sides, then both parallel sides in a given pair have equal length. Let me draw that a little better. Let me draw that better. Okay. So it turns out that in this case, this pair of parallel sides has equal length, and this pair of parallel sides have equal length. And of course, these categories overlap also. So it turns out that, I mean, all rectangles are parallelograms, right? Because if you have a rectangle, the two sets of sides are parallel. And then all rhombi, which is the plural of rhombuses, these are also all parallelograms. Turns out if you draw a rhombus with four equal sides, then the two sets of opposite sides are always parallel. So if you have a rhombus or a rectangle, they're both also parallelograms. There's a lot of overlap between these categories. And then we have trapezoid, which is a little controversial. Different people have different definitions here, but I prefer this definition, which is a quadrilateral with at least one pair of parallel sides. Some people will say a trapezoid has exactly one pair of parallel sides. That definition can sometimes be useful, but I prefer this, that it has at least one pair of parallel sides. And that means all parallelograms are trapezoids, but more often you have something like this. This is what's going to give you a trapezoid, and these are your parallel sides over here. Okay. And then there's also just other quadrilaterals that don't fit into any of these categories, kind of like this one that we drew over here. So this doesn't have parallel sides. Its sides are not equal. Its angles are not equal. It's just a random quadrilateral. And when you have that, that's usually just called a quadrilateral. In some places, I've seen the word kite used for this, but it's not a standard word. Usually you just call it a quadrilateral. You could call it an irregular quadrilateral. You could probably even call it a scalene quadrilateral if you wanted to do that. So, but in any case, it's just a quadrilateral. But usually the quadrilaterals we'll look at will be, quadrilaterals that have some sort of special property here. All right, any questions about this? Okay. All right, good. Okay, so, all right, so let's do types of quadrilaterals. So I'll just mention, unlike a triangle, a quadrilateral can have an angle of over 180 degrees, just like this one that we showed, right? We have this quadrilateral from the problem, right? If this is, let me just try to draw it a little better. Let me draw this a little better. So if we have, right, so if we had this with 60 degrees and 15 degrees and 20 degrees here, then we saw that this angle here is 265 degrees. We calculated that. So this quadrilateral would be what's called non-convex because it has an angle greater than 180 degrees. If you have a more standard quadrilateral, something that looks like this would be called convex because every angle here is less than 180 degrees. What convex really means is that if I take any 2 points inside the quadrilateral, I can connect them with a line that stays completely inside the quadrilateral. Whereas over here, if I take, this point and I try to connect them with a line, then that line is going to go outside the quadrilateral. So convex in general in geometry means that if you have any 2 points inside and you connect them with a line, that line stays inside the shape. Okay, that's what convex means. And so for quadrilaterals, being convex is the same thing as having all of your angles be less than 180 degrees. Less than 180 degrees means you kind of keep bending forward. You don't have any bending backward like this. When the angle is over 180 degrees, that means it's bigger than a straight line, which means you have to bend backward to make an angle over 180 degrees. When you bend backward like this, you end up getting a non-convex quadrilateral. You get 2 points where the line between them goes outside. Okay, and with triangles, of course, you can't have an angle over 180 degrees because for a triangle, so I'll answer your question in a second. So a triangle, every angle is under 180 degrees because they add to 180. So a triangle is always convex. So Tony, to answer your question, convex means if you have any 2 points inside the quadrilateral and you connect them with a line, then the entire line is inside the quadrilateral. Non-convex means you can find 2 points where the line between them passes outside the quadrilateral. Okay, that's what non-convex means for your quadrilateral. And a way to test for it is that convex means that every angle is less than 180 degrees, and non-convex means that there's going to be some angle that's bigger than 180 degrees. Okay? All right, any questions on this?
So,
Yep.
so we can say if we have a reflect angle in the quadrilateral, that is a non-convex. Right?
Yeah, so sometimes people use the word reflex angle for an angle that's bigger than 180 degrees. Yeah, exactly. That will mean that it's non-convex. And you can only have one of those, right? Because you can't have 2 angles that are more than 180 degrees because then your total angle measure would be more than 360, right? So at most you can have one of these so-called reflex angles, which means an angle bigger than 180 degrees. All right, other questions? Okay, all right, so let's move on. So we have area formulas for our special quadrilaterals, right? So we know that a square of side length s, that the area is equal to s squared. This is just a square with side length s. We have a rectangle with side length L and width W. We've already seen this. The area is length times width. So it's L times W over here. This is the diagram. So this would be L or this would be L and this would be W. A parallelogram with base B and height H. We've already seen this. So if this is H, let me do that in another color. So if this is the height H and this is the base B, then the area is just equal to base times height. So these are all things we've seen, so I'm writing them smaller. And then the trapezoid, I'm going to draw a little bigger because this is somewhat new. So if we have a trapezoid and it has parallel sides of length B1 and B2, and its height is H, then it turns out that the area of the trapezoid is equal to the average of the 2 bases. So we take B1 plus B2 divided by 2, and then we multiply this by H. Okay, so this is the area formula for a trapezoid. This is the new formula. Okay, and why is this true? Well, let me give you a little proof of this. So what I'm going to do is I'm going to draw lines like this from the top corners of the trapezoid down to the bottom that make right angles here. And I'm going to call this little bit over here X, and I'm going to call this little bit Y. And remember that B1 here is the entire base. So what do we have? The area is equal to, let me give these little parts of it names. The triangle is A and the middle rectangle is B and this other triangle is C. So the area is A plus B plus C. Well, what's A? A is a right triangle with base X and height H. So that's 1/2 XH. Now B is a rectangle with height H and width B2, right? So this would be plus B2H. And then C over here is a right triangle also with height H, right? All these are H. And the other side is Y, so base is Y. So we have plus 1/2 YH. And what is this? This is equal to 1/2 X plus 1/2 Y plus B2 times H. And what is 1/2 X plus 1/2 Y plus B2? Let me say what this is. We can write this as 1/2 X plus Y plus B2 plus 1/2 B2 times H. Right, all I did was break this up so that I pulled off half of the B2 and put it into this term, and I left a remaining 1/2 of the B2 over here, right? So this is 1/2 X plus 1/2 Y plus 1/2 B2 plus another half B2. But what's X plus Y plus B2? That's just the length of this side. So that's just B1. So this ends up being 1/2 B1 plus 1/2 B2 times H, which is exactly the formula that we want to have, right? So this 1/2 B1 plus 1/2 B2 times H, which is exactly this formula over here. Okay, so if you want this one a little bit fast, but if you want a proof of the area formula for a trapezoid, well, this is your proof. Okay, so the area is, you can break it up into a right triangle here, and a rectangle here, and another right triangle here. This right triangle has area 1/2 XH. This rectangle has area B2H. And this right triangle has area 1/2 YH. And if you combine them up and do some algebra, it turns out to give you exactly this formula over here. Okay, so this is the area formula for a trapezoid. You have to take the average of the two bases and you multiply it by H, by the height, okay, which is the distance between the two bases. Okay, the bases are the parallel sides. Okay. All right, any questions on this? Okay, and for a general quadrilateral, there are some more complicated area formulas, but I'm not going to get into them for now. I mean, usually when you're trying to find area, it's going to be one of these special quadrilaterals. Okay, a square, a rectangle, a parallelogram, or a trapezoid. Okay.
Hello, Dad.
Yes, Ed.
Hello. I
Yes.
have an observation from the formula.
Mm-hmm.
In the typical formula, I have A is half XH plus B2H plus half YH.
Mm-hmm.
And because I saw the general formula saying that the area is equal to B1 plus B2 over 2 modulo over H.
Mm-hmm.
Okay, from this diagram here.
Yep.
What if X and Y is not equal? Can I use that formula?
Yeah, they're not assumed to be equal. That's why I used two different letters. That's why I didn't just call them X and X. So X and Y are not in general equal.
Yeah,
that's totally fine.
Yeah, then for B1 now, because if what one are not equal, because I noticed that B1 is equal to X plus Y, right?
No, B1, yeah, so maybe this is what I have to say. B1 here is equal to X plus B2 plus Y, right? Because X is just this part over here, and then this part between the two right angles is the same as B2. And then you have Y over here. So B1 is in three pieces. It's X plus B2 plus Y.
Oh, okay, that's okay.
Yeah.
Thank you.
Yeah, so maybe let me label this a little clearer. So this X really goes from, X is really just this, and Y is really just this. And then this over here is really B2, because it's the same as the other B2. Maybe I think that last B2 doesn't make the diagram clearer, but the point is this distance here is B2. Okay, other questions? And that's why this formula works. That's why when I have 1/2 x plus y plus b2, I can substitute b1 in that formula. Okay. Other questions?
Yes.
Yes, James?
Yes.
James,
So,
a question?
yes. Are you done?
Oh, I'm getting you, but it's not so clear. It's a little distorted. Yeah. Maybe it's better if you type your question into the chat because it's not so clear. All right, let me move on for now. So another alternate area formula for a rhombus. So you can do this with a real proof, but for now I'm just going to draw a picture. So if I draw a rhombus like a diamond, if I draw the diagonals, so these are the lines that connect the two opposite corners, it turns out that when you have a rhombus, these actually make right angles everywhere. Okay, so these make right angles. And so if each diagonal has length d1 and d2, then what's the area of a rhombus? Well, so in this case, this would be basically, d1 over 2, and this here is d2 over 2. Let me actually, let me draw this picture a little better. So let's say we have, okay, if I have a big rhombus, just so we have a little more space. So I have a rhombus, and I draw these two diagonals. They meet at right angles. Okay, so this is a right angle here. And then if the diagonals are d1 or d2, this here is 1/2 d1, and this is 1/2 d1, and this is 1/2 d2, and this is 1/2 d2. Okay? And so what do I get? So the area is equal to the sum of the 4 triangle areas. And these triangles are all congruent. They're all the same, right? Oh, sorry, I see, James. The sum of the 2 parallel sides divided by 2 is equal to the area. Yes, James, that's exactly right. So this, which is 4 times 1 triangle area. And what is this? It's 4 times, well, each one of these triangles has area 1/2 the base times the height. So that's 4 times 1/2 times the base. The base itself is 1/2 d2, and then the height is 1/2 d1, right? This over here is, this is the base, and this over here is the height. And if you multiply this all together, what do you get? You get a 4 and a 1/2 and a 1/2. These all cancel out, and you're left with just a 1/2. And so what this ends up being equal to is just 1/2 times d1 times d2. So when you have a rhombus, you have this alternate area formula, which is given by 1/2 d1 d2. So if you know the diagonals of a rhombus, then you can get this area formula with just taking the product of the diagonals and then multiplying by 1/2. Okay. All right. So any questions about how we get this formula? Yes.
Where you using 4 times one formula of one of the triangles, so that is a similar triangle in the box.
Yep. So right, 4 times, because it's 4 triangles, right? So if I know the area of one triangle, I can just multiply it by 4. So I have 4 over here for the 4 triangles, and then each one triangle is 1/2 times base times height. So it's 1/2 times the base, which is 1/2 d2, times the height, which is 1/2 d1. So that's why we have all these 1/2s. It's 1/2 times the base times the height. And then the 4 cancels out with 2 of the 1/2s. So they all disappear, and we're left with 1/2, the remaining 1/2 times d1, d2. Is that okay?
Hello, sir.
Yes, hello, Prince.
Yeah, my question is this. For instance, if we have one diagonal into this ribbon, can it make the formula to be set?
So if you have one diagonal
One
here,
diagonal into the ribbon, can the formula be proven, or can it be set equal to this, or do we have different formula to it whenever you have one diagonal into the ribbon?
yeah. So, I mean, if you have a rhombus, I mean, you need both diagonals in order to get the formula for a rhombus. And if you have a parallelogram, you have to take a variation of this formula that uses some trigonometry. There's going to be a sine of the angle between them also. And we're not really doing trigonometry, so I don't want to get into that right now. But for the rhombus, you really need both diagonals to be able to use this formula.
Okay, thank you.
Okay, you're welcome. Okay, so let's do, we have a little bit of time left. So let's do, I'm going to just skip, well, maybe I'll say something quickly and then maybe we'll be able to do one problem. So for a trapezoid, you can also draw what's called the median. So if I have a trapezoid like this, I can take the line segment connecting, so these are called legs, the non-parallel sides. So these are called legs. Right, these sides are called legs. And I can connect the midpoints of the two sides. This is called the median of the trapezoid. And let's say that this has length b. And then it turns out that the length of this median, right, if this is b1 and this is b2, and the trapezoid has height h, then it turns out that the length of this median, you can also just write that the area of the trapezoid, since the median is exactly the average of b1 and b2, then you can also write the area of the trapezoid as bh, just like for a parallelogram. The only difference is you've got to take b here to be the median of the trapezoid instead of just one of the two bases. It needs to be the median. Okay.
So, hello,
Yes.
Omer?
Yes.
Taking the median that is there, in case the B1 is given, the B2 is given, the value is given now. So are we going to add the both of them to stand for the median?
When you add both of them and divide by 2, you get the median. So you're taking the average of the two bases, and that's going to give you the median.
Okay.
And I mean, I can prove that. I'm not going to prove it now because we don't have time. But if you look at the picture, it seems at least reasonable that this length should be kind of halfway between this length and this length, right? It should be right in between. It's going to be the average of the two. Okay. So not really going to use that. So I want to take enough time to do one problem. So let's do an exercise. So a rectangle has area equal to 40 and a diagonal of length 10. And the question is, what is the perimeter of the rectangle? And so remember that the perimeter, so if I draw this rectangle and I label the sides with length x and y, recall that the perimeter is equal to x plus y plus x plus y, or in other words, 2x plus 2y, right? Because this is x and this is y. So the perimeter is what you get when you add up all the sides of the rectangle. Okay, and so this question gives you a diagonal, right? So you may as well draw the line that the question refers to, right? So that's the diagonal. And so what are we given over here? Well, we're given that the area is equal to 40. So our area formula right here is given by xy, right? Area is given by xy. We're also given that the diagonal, so if we the diagonal, let's say the diagonal is equal to d, which is equal to 10. And what equation do we have? If this is d, what equation do we have that relates d to x and y? Right. So by the way, James, yeah, that's also correct. You can factor out the 2 if you want, 2 times x plus y, or if you want to call them h and w, that's fine too for height and width. So what equation do we have that relates the diagonal to x and y?
Yeah.
Yep.
Hello?
Hello, yes?
Yes. Yeah, since the rectangle is, the different corners are, the total angles there is 360, and we believe that each corner angle is equal to 90 degrees. You can use Pythagoras theorem.
Exactly.
Because the diagonal divides the rectangle into 2, right angle triangles.
Mm-hmm. So what angle does Pythagoras then give us? What equation does Pythagoras give us?
It says that c squared is equal to a squared plus b squared.
Right. And so the way this is labeled, we have x, y, and d. So we'll write it instead as d squared equals x squared plus y squared. Right. Great. So what do we know? We know we have 2 equations. We have 40 equals xy, and we have 10 squared equals x squared plus y squared, or 100 equals x squared plus y squared. And we want to know, what is this perimeter? We want to know 2 times x plus y. We want to get that. We want to get that quantity. So the question is, if we know what xy is, and we know what x squared plus y squared is there a way that we can figure out what 2 times x plus y is? And there's going to be kind of a harder way and an easier way, but the easier way is a little bit tricky.
Yeah, I think there is a way we can find 2 times x plus y.
Yes, how can we do that, Clinton?
Okay, so we write x squared plus y squared in this equation. 100 equals s.
Yep. Sorry, I'm not getting you now.
Plus y squared. We write x squared plus y squared as parentheses x plus y equals all squared square.
Okay.
Xy now with 40.
So sorry, so x squared plus y squared here, we're going to write as x plus y squared minus 2xy.
Yeah, sure.
Right. Okay. Good. And now we're subbing in 40, right? So this is x plus y squared minus 2 times 40, right? So I'm running out of space a little bit. Let me just finish over here, right? Because 40 is equal to xy. So we have 100 equals x plus y squared minus 2 times 40. So if we add 2 times 40 to both sides, right, we end up getting 180 is equal to x plus y squared. Okay, so how do we continue from here? Yep, so where do we go from here? So 180 is equal to x plus y squared. Great. And we want to know 2 times x plus y. Well, let's see, if 180 is x plus y squared, right? We can figure out x plus y, right? So square root of 180 is equal to x plus y. And that means our 2x plus y, which is the perimeter. So 2 times square root of 180 is equal to 2 times x plus y. And this is this perimeter. This is this p that we want, right? Okay, great. So this is our answer. So our answer is, in fact, it's 2 times square root of 180. That's going to be the perimeter. And if you want to simplify this, you can pull out 180 is 36 times 5. So you can pull out a factor of 6 if you want. So you can write also this is equal to 12 times square root of 5, if you'd rather write it like that. But I don't really care if you simplify your radicals, and 2 times square root of 180 is perfectly fine. So yeah, so this is a little bit tricky, right? So Clinton had the right idea, which is you're given xy and you're given x squared plus y squared, you have to somehow get x plus y from that. So you could try to do a substitution and then solve an equation, but that's actually going to get pretty complicated. So the faster way to do this is to recognize that both of these are going to show up as parts of x plus y squared. So if I have x squared plus y squared, I can rewrite it as x plus y squared minus 2xy, right? Because I have to subtract off the extra 2xy I'm going to get from this. And since we know what xy is, that's just x plus y squared minus 2 times 40. So we have that 100 equals x plus y squared minus 2 times 40. And once we have that, you get that x plus y squared equals 180. And then you can solve for x plus y. And then you can solve for 2x plus y. Okay, so this problem is pretty tricky. You have to do a lot of things. You have to use the Pythagorean theorem. You have to then find this creative substitution in order to solve for x plus y on its own. And then you carry through all of the math, and you end up getting 2 times square root of 180, or 12 times square root of 5, which is the same thing. Okay, so it's a bit of a tricky problem. Right, any questions on this?
Yeah, Mr. Overall.
Yes.
The 2 outside the radical sign there. Where do we
Yes.
get our 2 from?
Oh, well, it's just we want to multiply both sides by 2, right? We have that 180 is equal, root 180 is x plus y, but we want the perimeter. And the perimeter is not x plus y, it's 2 times x plus y. So we have to multiply it by 2 in order to get the perimeter. Right, I mean, we solve for this quantity x plus y, but what the question asks for is this perimeter, which means we really want the quantity 2 times x plus y instead of x plus y. Does that make sense? Okay. All right, so for matters of time, I'm going to leave this as an exercise. Maybe we're not going to do this together. You can do this for extra homework if you want. So diagonal of a rhombus has length 16, and each side of the rhombus has length 17. Find the length of the other diagonal, and just my hint is just try to draw a picture. So if this is 17, I mean, all of the sides have length 17 because it's a rhombus. And if I have one diagonal here that has, you know, if this diagonal here has length 16, then the question is, can you find the other diagonal? Okay, so that's going to be, oh wait, let me draw this the other way. Let me draw this the other way. I don't think it's going to be the longer one. Let's say this one has length 16. And then the question will be, what is the length of the other diagonal? Okay, so this we're going to leave as an exercise. And then, so there's going to be a bunch of quadrilateral exercises because you've got 2 weeks, right? You need something to do during Christmas and New Year's, right? So, so here's our 2 exercises. So the first one is the diagonal of a rectangle has length 37, and the length is 1 less than 3 times the width. What is its perimeter? And the hint is, if you let x be the width, then you can set up an algebraic equation for x. And once you know x, then you know the length as well, and then you can figure out the perimeter. So I'll leave that just as a hint there. Number 2, find the area of a rhombus with sides of length 13 and one diagonal with length 24. And you're probably going to want to use the diagonal area formula. And then lastly is to find the area of the following trapezoid, which I'm going to draw for you. So here's a trapezoid. So this side here is length 20. This side has length 15. This side has length 13. And I'm going to draw just this right angle over here. And I'm going to say that this here is 5. Right, so this is this little part right here is length 5. And so the question is, can you find the area of this trapezoid? Okay. So that's going to be, this is a nice, this is maybe, this is multi-step. It's maybe a little bit tricky, okay? We can call this a challenge. Okay. Okay, so these are for homework, and then number 4, you can do this this exercise on the previous page for number 4. Okay. So this is all that we're going to say about quadrilaterals for now. And then remember, next week there's not going to be any class. So December 29th. So we'll take a break for Christmas and New Year's vacation. And then on January 5th, we're going to come back and we're going to discuss general polygons. So polygons with end sides, right? We did triangles and quadrilaterals. We're not going to have a day about pentagons by itself. We're just going to have one day where we talk about general polygons, and then we'll move on to circles. Okay. So, all right. But I think that's good for today. So want to remind you, please type your name in the chat if you have not done so yet. I want to make sure that I have everybody's record for attendance. And I want to wish everybody, a very happy holiday season, a Merry Christmas, and a Happy New Year's. I've had a great time doing this math for 2023 and looking forward to 2024. So we'll start back up in a couple of weeks.